thank you for the introduction. Hello, everyone. We'd like to thank you, NVIDIA, for giving us the opportunity to present our work in this important. As stated earlier, I am Eduardo Cabrera, and on behalf of my colleagues, I'm presenting our work entitled Accelerating the FALL3D Flagship Code, Insights from Porting a MiniApp. We'd like to thank as well to our mentors at the Shineka Hackathon in June this year, Piero Lanucara from Shineka and Lucas Mosiman from NVIDIA. These activities are part of the CHEESE project, that is an EU-funded Center of Excellence for Exascale in Solid Earth. This is the agenda of this talk. First, I'm going to tell you briefly about our scientific application. FALL3D, in a nutshell, is a CHEESE flagship code developed and maintained by the Barcelona Supercomputer Center and the National Institute of Geophysics and Volcanology in Spain and Italy, respectively. It uses an Eulerian model for the atmospheric transport and deposition of particles, aerosols, and radionuclides. It solves a set of attention diffusion sedimentation, or ADS, equations on a structured grid using a second-order finite volume, and a special scheme could be either an Euler or Runge-Kutta fourth order in time. One of the objectives of this CHEESE project is to prepare these flagship codes, including FALL3D, of course, for the coming ACCelerating system. So it's mandatory to accelerate these flagship codes. Let's move into how the full FALL3D application is composed. It is composed by circa 100,000 lines of codes, organized in many different modules like the following: parallel, grid, domain, source, F3, ADS, physics, among others, and all tags like TGSD, source, FALL3D, DBS, FALL3D, which runs the FALL3D solver, or all, which runs all the previous tasks. Let me continue how the full FALL3D is implemented and the profiling campaign that was performed to identify its hotspots. The full FALL3D application is implemented in Fortran 90, and the CPU-only version uses plain MPI parallelization for domain decomposition. This 8.1 version is ported to accelerators, specifically GPUs, which is the focus of this talk. OpenMP is introduced as some version of the code. Later, I'm going to explain a bit further about this. When the time to optimize the application came, we have to decide which strategy and tools we are going to use. So OpenACC was selected because it's not necessary to modify all the code, just inserted a bunch of directives in the right place, and it will be easy to keep developing and maintaining it, I suppose, since only one source code is used. Furthermore, the characteristics we like it most are the ones listed here: flexibility, portability, and performance. Not in any particular order, anyway. Specifically talking about performance, the performance that can be achieved using OpenACC is a fairly good point on talking in favor of OpenACC. Before porting and optimizing the full FALL3D application, a profiling campaign was performed to identify the most consuming part of the code. Such campaign is not stated right here. The full FALL3D application was ported initially using OpenACC and adding some OpenMP directives. This first version was ported during a GPU hackathon at Shineka in 2019. The porting was limited only to a task FALL3D and only in the module ADS, specifically the Runge-Kutta for order. A trade-off was made between computing and memory requirements. This porting implied as well a full refactoring of some arrays and the way they are accessed. This version was taken on Power 9 at BSC, which has 4 GPU cards, NVIDIA cards, and 300 NVIDIA cards per node. This version of after the hackathon in 2019 was evaluated by POP. POP stands for Performance, Optimization, and Productivity, which is an EU-funded Center of Excellence in High-Performance Computing. The results shown that the full FALL3D application is very efficient at MPA level, and its load balance is almost perfect. The phishing analysis clearly points to the CUDA parallelization, or more concretely, to its loads balance here. This loads, yes, here. The efficiency analysis, yes, to the bottom, which is somehow expected as only a fraction of circa 27% of the iterative loop time is computed by the GPUs, which means that the GPU capacity is pretty low. Currently, as I said, As already stated, at the moment the GPU occupancy is per load. GPUs are computing only 27% of the iterative loop time. As only a minor fraction of the full app is ported to GPU, OpenMP directives were included to try to take advantage of the idle CPUs. Unfortunately, this does not provide enough gain in execution time. However, this full FALL3D version, GPU version, is almost 4 times faster than our reference CPU version executed on Mare Nostrum 4 at BSC as well, even in that state of development. This version was tested on a real test case scenario on Marconi 100, which has a 4 GPU NVIDIA V100 cards per node. This is the characteristics of the real test case scenario. And the graph shows that in every case from 16 up to 64 nodes, the full FALL3D GPU version that uses MPI plus OpenACC plus OpenMP within node is better than the plain MPI version. The MPI version is the GPU one. However, there is a marginal gain in 128 nodes compared to 64 nodes. After the previous performance results achieving the first GPU optimization at CENECA Hackathon in 2019, a new profiling campaign was done to identify where the issues or bottlenecks performance are. Let's get right into it. This profiling was done using SCORP at Marconi 100 during this hackathon. It is worth noting that according to this report, OpenACC used less than 5% of the execution time, whereas OpenMP almost gets 90% of it. Again, we clearly see that GPU occupancy is pretty low. Looking at the profiling report in detail, some areas were identified. 3 of the 4 top use OpenMP, so we decided to get rid of OpenMP, replacing them with OpenACC directives. All spotted areas are do loops. The first one is part of the module ADS solver, and the second one is a 4-nested do loop. The top 2 areas represent almost, these 2 areas represent almost an 80% of the execution time. So a MiniApp, which includes circa 90% of the computing time for the full FALL3D, was developed with a twofold purpose and a cheese context. Explain it further in the following slides. The MiniApp FALL3D only solves a task FALL using a fixed problem, which is a helicoidal velocity field. This MiniApp FALL3D has almost 10,000 lines of code and represents around 90% of the computing time of the full FALL3D application. This is implemented using MPI plus OpenACC plus OpenMP as in the previous version, as well as the full FALL3D. This MiniApp FALL3D is composed by only a few modules, tasks, like grid, parallel, domain, ADS, F3D, among others, and just a couple of tasks from the full app. This is the FALL3D and the helicoid that I already mentioned. The development of implementation of this MiniApp is part of 2 activities of this CHIS project. The development of this MiniApp FALL3D is related to CHIS co-design activities, whereas the porting and optimizing this MiniApp to OpenACC belongs to an optimization task within a CHIS project. We take advantage of this MiniApp FALL3D to accelerate through the NVIDIA Hackathon at CENECA in June this year. So the GPU strategy we follow accelerating the application to a MiniApp is explained in next. First of all, a quick NC filing was done through the shown command line at Marconi 100. This command line, using this version of the HPC SDK compiler. This profiling was done disable any output, reducing the number of iterations, adding NVTX markers, which is another tip from our NVIDIA mentor, Lucas Mosiman. And this green area was identified. It represents only 1 iteration of the simulation, which clearly shows that there were redundant data transfers in such region, and the strategy was to try to eliminate such redundancy. Furthermore, it's necessary increasing the GPU occupancy till that moment there were, as I said, circa 27% of the full iteration time. This implied to reorganize some of the code and replacing, as stated before, all OpenMP directives with OpenACC ones. It is worth noting that we never try OpenMP offloading. So one of those do loop is one for nested loop. The final code of this is shown in this image, which seems fairly simple, but it took a bit of effort to get it. But the main job accelerating this MiniApp FALL3D is explained in the following slides. One of the most important suggestions that our NVIDIA mentor Lucas Bosselman told us was to try to have only one big GPU region, kernel, instead of many kernels among CPU regions. That this implies reducing those data transfers already mentioned. Recalling the profiling report, the model ADS is the one that consuming the most execution time, circa 60% of the execution time. This ADS solver algorithm is characterized by solving the 3D problem in a 3 independent 1D subroutines, one per component as shown in this AD solver along subroutine Z, Y, and X. So the strategy is to fusion all the GPU, the strategy is to fusion all the GPU regions inside these 3 subroutines, 3 model subroutines of ADS, and fusion all kernels into only one large kernel. For example, we fusion this one and create this large region. We fusion this with this one, create this one, and finally we fusion all of them and get it only one big region, large GPU region. The first image of this slide is an actual copy of the data of the only one large GPU region before the main loop, along with the I-send and I-receive routines with the CUDA-aware MPI directives. Only one call to them was implemented during the hackathon in only one subroutine mentioned earlier, specifically the ADS solver along X. In the following days after the hackathon, the rest calls to such I-send and I-receive subroutines were implemented in the other 2 subroutines stated. The solver along Y and Z, and in a couple of subroutines more. These images show the actual state of the accelerated code at the NVIDIA Hackathon in Shineka in June this year. Talking about some issues and requests that we have to the OpenACC community and so on. As William Sayer stated yesterday, the good outweighs the bad and the ugly. Yeah, however, at least for us, we found the following issues. The first we were using HPC SDK 2020 and 21 version, but I tried the GNU compiler that is supposed to support OpenACC. However, after a couple of hours trying to compile it, I quit. I was unable to compile the code using that GNU Fortran compiler version on Marconi 100. The second issue was that OpenMP did not show up on Marconi 100 in the NC's profiling, even though we specify it with the -T OpenMP flag. Shineka is already aware of this issue that seems to happen maybe only in power systems. Finally, more than an issue, is a request or desire that we have. When we try to use the deep copy feature of OpenACC Fortran in the MiniApp, which one of the approaches, the implicit attached behavior that we use, we couldn't find it, even in searching through many tutorials, material from different HP centers and different sites and so on, all over the web. Even our media mentor during the hackathon couldn't advise on this. He actually asked during the second or third day, I cannot remember exactly well, asked for some Fortran expert and who couldn't help us either. This lack of documentation also applies to the CUDA-aware MPI feature. At least this is our experience. So the request is not only, as Professor Chapman stated before, that better compilers and better environments, ecosystem. The request is to have at least a really well-documented material tutorial or whatever you name it. Such documentation could be quite hard to update in a printed version. However, not as an electronic material. So, for example, when you click the theory, another click goes to the access a brief example. Another click allow access a deeper or detailed example, and even the timeline when such feature was added to the standard could be displayed as well. There were only kind of frustrations on the path accelerating this MiniApp, but fortunately everything goes well. So the test case scenarios and the results are presented in the following slides. So this is the test case scenario used for assessing the ported version of the Mini FALL3D application. Grid implies grid cells on each component X, Y, Z. We tested 3 different domain decomposition scenarios from 4 processors up to 64 processors with the following configuration per component again. Finally, all these test cases were executed on Marconi 100 at Shineka, which has the following characteristics. We use this version of the HPC SDK compiler, and we tested from 1 up to 16 nodes of the machine. This is the performance achieved with the MiniApp FALL3D in the strong scaling test case. This graph shows the performance using 3 different versions of the MiniApp. The first one is the plain MPI version in brown. This is just as a reference. The second one in blue is the version after the first GPU hackathon at Shineka in 2019. This version uses the full FALL3D application and uses MPI plus OpenACC plus OpenAP with a node. And finally, the third case in yellow is the actual version of the MiniApp of FALL3D after the second hackathon at Shineka in June this year. This version uses MPI plus OpenACC, including CUDA-aware MPI. As we can see, it seems that there is not enough workload using more than 2 nodes in this strong scaling test case. So we try a new case, which is something like a weak scaling. However, strictly speaking, it's not a weak scaling since there is not a totally constant workload per processor. Since the finer the domain decomposition, the longer it takes to compute it without violating the CFL condition. Anyhow, this is performance achieved with the MiniApp in this case. The first graph shows the execution time using 1 node up to 16 nodes. It is using 64 GPU cards. It is not a very good performance achieved. So such time is divided by the number of iterations and normalized to such results using only 1 node. And so we get the second graph of this graph, which is in the bottom, which shows that a good performance is achieved in this so-called weak scaling test case. The second to last item on the agenda is the conclusion of this talk. So that are the following. The MiniApp FALL3D only solves task FALL3D assuming a fixed problem, which is called a velocity field. OpenACC is used to speed up both the full FALL3D and the MiniApp FALL3D. The current MiniApp GPUs are computed 100% of the time of the iterative loop time compared to the 27% of the first porting in the Shineka in 2019, the hackathon at Shineka in 2019. The MiniFALL3D app was successfully tested on both strong and weak scaling. Well, the latest MiniFALL3D GPU version uses MPI plus OpenACC, including CUDA-aware MPI. It's 7 times faster than the previous version, which uses MPI plus OpenACC plus OpenAP directives on a medium-sized problem of this size. A speed of 29 times has achieved versus the plain MPI version after 2 NVIDIA hackathons, the one in 2019 and the one in this year. All these speedups were achieved using double precision at Shineka hackathon on Marconi 100. As I already stated, but it's worth mentioning again. So finally, the future word is we are merging the MiniApp FALL3D into the full FALL3D. This process will increase the amount of required resources, specifically memory and execution time when dealing with real test case scenarios, one I showed previously. And we are looking forward to the next GPU hackathon to accelerate this merge full FALL3D version. That's the end of my talk. Thank you very much.